Dattaraj. So I'll talk about the second part after Dr. Mukta's focus more on bias and accountability. So I'll focus on reproducibility and transparency, which are also very important pillars of our responsible AI strategy of any company. So reproducibility talks more in terms of when you're building machine learning models. As you're building models, how do you make sure across different data scientists there are multiple preferences that each has their own preferred library, each has their own preferred way of programming, way of developing models. How can we standardize this? This is something as ML is growing, as every field is getting influenced by machine learning and artificial intelligence. This is becoming a major need in the market. How do we standardize, make your experiments reproducible? And just like you have in software, you have a DevOps cycle. How can we focus on an ML ops cycle where you are applying the principles of DevOps, agility to machine learning so that your experiments are reproducible? Plus, you have the concept of an experiment. So typically you have, when you're doing software development, it's very deterministic. You check in your code, the CI/CD pipeline triggers, and your code starts building. But in ML, there is a concept of an ML experiment. You have to know the data, the source of the data, how you have to do a lot of, like Dr. Mukta had shown, a lot of effort is spent by data scientists, not in the actual algorithm development, but in actual data cleansing, feature engineering to actually build a model. So reproducibility becomes very important there. And then, like we had these examples where the model actually had bias. I mean, no company intentionally wants to introduce a bias, but because the data has the bias, that comes into your model. So how do you check for that? Can you use some way to explain your model, find out if there is a bias? So those are the things that typically are into the transparency pillar. So let's start with reproducibility. Now, like we said, with the modern ML ops pipelines, it's more than actual just building an algorithm. So there are four, at a high level, at a conceptual level, there are four things that a data scientist typically has to focus on. Data management, where you have to look at the data, cleanse the data, make sure the data is good quality before you use it to build a model. Of course, the core model development, and deploy, taking the model, I mean, you have to choose between different models, do hyperparameter tuning. And then the selected model, you are deploying that to production. So you need to have a system. You cannot be building a new deployment system for every model. You need to have a system. And today, the most popular way of deploying models is using microservices. So microservices-based system where the model can be deployed as an API and can be invoked through a client application. That is very important. And then when you do the deployment, there are a lot of other considerations. You want to do things like A/B testing. In fact, now mature ML organizations are even doing multi-arm bandit. They are trying multiple models at the time and using almost concepts of reinforcement learning to make sure you get the right model to the right customer base. And then overall, a model lifecycle becomes very important. How do you track what is the version of the model in production? And when a new model comes, how do you compare them? So there are tools, there are a lot of open source tools that have matured in the recent years. Things like Open MLflow, PyCaret, which address each of these stages in your ML development cycle. And I'll cover some of these. So I'll focus on DVC, which is data version control. Then PyCaret, and at the end of this half an hour, I'll show a demo of a reproducible ML pipeline having some of these tooling like PyCaret, MLflow, and then using some of these methods to deploy a model and deploy a model to a model registry. Now, as you know, there are a lot of these cloud offerings like AWS Data Studio or Databricks or SageMaker. Now, these systems are kind of inbuilt. They address all these four stages. So even if whatever the tooling you use, I mean, you may use Spark or you may use regular Python, TensorFlow, PyTorch, the patterns remain the same. So what I'll focus is more on the patterns of each of these four stages, because your technology stack may be diverse, but as long as you can focus on some of these patterns, I think that can be reproduced. These patterns can be reproduced in any programming technology stack, and then you can your ML ops cycle should kind of try to focus on some of these reusable patterns. And let's talk about some of these patterns. So in data management, definitely a data ops pipeline. You would want to have a pipeline where you want to clean data, especially if you're not getting quality data. You want to do a lot of feature engineering. And now a pattern which is popular is a feature store, where you have fixed rules to clean your features and make those same features available both for training and for inference. A version data catalog is highly recommended. we have seen the stage where we have CSV files to build models, but then you have to have a version control for the CSV file. So a tool like DVC, data version control, and again, this is just a pattern, data catalog. You can use DVC, you could use a different tool for this. Same goes for all the patterns that we'll talk about. But DVC, what it does is it puts an encapsulation layer or an abstraction layer in front of your data. So your data could be in S3, your data could be in Google Drive. You access it the same way, and it will manage the versions of the data. So that's pretty popular. Data quality is very important because you want to make sure your data is complete, accurate. You want to clearly know the missing values and what to do with them. Model development, AutoML is becoming very popular, where instead of you manually training multiple models, you want to be able to have a tool which can automatically use the same data, train on multiple models, and give you a list. So we'll see an example of this with PyCaret. And now we are seeing a lot of growth of low code and no code ML tools. So things like PyCaret, which are low code, where the data scientist has to write minimal code, just set up the experiment, and the system behind the scenes does a lot of the groundwork and gives you some clean results, including plots. And then for production deployment, like I said, we do want to look at how A/B testing can be done, multi-arm banding. So there are tools like Seldon, which can help in this. And for the life cycle, there are patterns like model registry, model monitoring, and we'll see model registry in MLflow. So you want to be able to version the model, keep it in the registry, and then make sure you can retrieve the right version for the right production system. So long story short, these are the 4 stages of your MLOps pipeline, typical stages in an MLOps pipeline. And there are different established patterns in the industry, and you want to, whatever the tool you use, you want to be able to have some of these patterns to address specific problems that you have. So let me take an example. This would be your typical, your current ML cycle. You will have an ML development environment and a production environment. A development environment is where you will do your data preparation, your model development, testing, and validation. And then once you're the data scientist, so this will be typically for the data scientist. Once your data scientists are satisfied with your statistical performance of your model, you would want to deploy it. So you would want to have an environment, either a cloud or on-premise, where so this is typically in today's world leveraging microservices. So you could use something like Kubernetes to package your model as a microservice on Kubeflow and deploy this. So you have your ML model running in production, and you have this logging service which comes with your production environment. So on the data science side, you would typically look at the statistical metrics, like you look at the confusion metrics, you look at the area under the curve or the ROC curve. And then on the production side, typically these metrics, if you look at Kubernetes, you can have tools like Prometheus to actually log these metrics and Grafana to visually plot them. These metrics are typically service level metrics, where they will tell you if your API was down for so long, of 24 hours, how many minutes or seconds it was down, and then how much how much data came in, how many API requests came in, what was the size of the request. So these are more like the service level monitoring of the metrics. So this is typically, I would say, how a traditional setup would look like. Now, let's see how we can add reproducibility to this. And again, I'm just focusing on patterns. So some patterns to add reproducibility to this setup. Number one will be a data catalog. So instead of you just having these CSV files with -v1, -v2, let's have a data catalog where, just like Git, you are managing versions of your data source. Now, this can be either done at file level, like a DVC, or if you have something like a Snowflake, which is more of a SAS ERP, you could actually do versioning of the data at the SQL level. So this query would give you version 1 data, this query would give you version 2. Now, Snowflake actually has a time travel feature. You can actually write your data catalog at a temporal level. So you can say, for data collected till this date, give me this as version 1 and till this date as version 2. So so modern tools have a lot of advanced features to do temporal analysis. But for this experiment, we just use DVC to version files differently. And DVC, like I said, will give you an abstraction layer. So I have my files on Google Drive in this demo. I'll pull them from Google Drive and show you the different versions. Model registry is another popular catalog. Like once the model is published, you're happy with the metrics, you want to push it to the registry. And then at the service level, now you are looking at service level monitoring. Now, we can add some transparency to this, where along with the service level monitoring, you also want to monitor for things like data drift and concept drift. So what happens is your model, once it is deployed as a microservice into production, it has been trained on some representative data set that you collected, some version 1 of the data set. But now over time, the situation changes. For example, with COVID, the pattern of data was totally, especially in retail side, was different. A lot of people were working from home. There was more internet traffic. People were buying at regular office hours because everybody was at home. So because of these changing patterns, you would see your data that you used to train the model is no longer representative of the production. So in that case, you will see like a decrease in accuracy of your model. So this will be the relationship between the target and your variables would change. So this will be a concept drift. And you can also detect this by data drift. So if there is a, like when you're working from home, there is a big increase in bandwidth during the day hours as compared to when people were in office, if you're an ISP. So you would want to, so you will see a change in distribution of the data. So you also want to monitor the data drift in production along with your service level metrics. And then you also want to have some sort of an explainability. Now, explainability becomes very important for transparency. And this can be done at 3 levels. So it can be something that when you select an algorithm, if you're building a model, you may want to select a more interpretable algorithm, right? Random forest. So something like a tree-based algorithm, which can be inherently explainable, you may want to select if explainability is very important. Or you may want to look at post-hoc explanations, where you may select the best model like an XGBoost or even a deep learning model. But then you want to have some system like LIME and SHEP to actually provide explanations. Now, this is where in our demo, we'll see an explanations that are generated on the model, which are part of your MLOps cycle. So we highly encourage that have this as a pattern where when you have an MLOps cycle, you want to also include explanations. And in your report, make sure that some of the results of the explanations and the fairness studies that Dr. Mukta showed earlier, those are also included in your MLOps cycle. So, and then the third level where explanations come in is at the inference level. When you are actually, once your model is deployed, you're making a prediction. You want to do a local explanation at that level where you want to know why a particular prediction was made. So in that case, it gets into more complex things like how can you explain an individual prediction? There are even things like counterfactual, where what if certain values change? Can you account for the change in prediction? So things like that. So it can be very detailed that way. But these are the 3 levels where you want to at least have some sort of an explainability as a sanity check in your MLOps cycle. And last thing, what Dr. Mukta covered in detail is basically the accountability piece. Now, this is, in my mind, the very most important piece. I mean, these are reproducibility, transparency, these patterns you can apply using tooling. But accountability is something more of a culture change for the organization. This goes back to the Mr. Subramanian's question also. Like, who is accountable for this? I mean, basically, if you are a vendor, you would want to have best practices to include some of these reproducibility, transparency into your MLOps cycle and have some sort of an audit mechanism. When you're delivering an AI, when you have your MLOps cycle, you would want to provide an audit mechanism when along with the model, you want to provide why some decisions were taken, what was the data set that the model used for. So a tool like MLflow can give you a nice audit report where it will tell, and I'll show an example of that audit report, where it will tell you what are the charts that, accuracy charts that came out, what are the fairness studies, and then why some decisions were taken. And then the committee also has to decide, like once you do the monitoring in production, so when the production monitoring is done, if you detect a concept drift or data drift, now typically it's a gradual transition where this data drift and concept drift happens, and your accuracy starts dropping. You want to decide at what time you want to trigger a retrain. So if the data accuracy falls below, say, 80% or 70%, you want to trigger a retrain. So that also should be designed by a human in the loop, and that's what the AI committee would do. So I would say AI committee is definitely recommended for a vendor who wants to make sure that your process is has all the audit metrics, and also for the customer who is ultimately going to be responsible for the output of your model. Whoever is ultimately responsible for the prediction that your model is making, they would want to set up specific requirements for fairness and bias for your ML model, and that would be something managed by the AI committee. So in a nutshell, these are the 3 initial pillars: reproducibility, transparency, accountability of responsible AI. And now I'll show a demo or a notebook demo of how some of these can be incorporated using tooling into our MLOps pipeline. And then Amog, in the last section, will cover the other two pillars, security and privacy, which are also equally or probably more important. So let me jump to the demo. So this is a Jupyter notebook I have, where what will show is just doing a check. You can still see my screen and I'm audible, right?
Yes.
Okay, cool. So so let me walk through this. So here, what we'll show is we'll show basically a couple of we'll show focus more on the data science cycle. So this is for the data scientist persona. So we'll use a data catalog to load data from an external system like S3 or Google Drive. It could be your own private VPC or Azure. And like I said, here it will be more of file based, but it could easily be a Snowflake database. And you load data into a data catalog, load a particular version of the data, I should say, build a model. So we'll use a low-code tooling called PyCaret in Jupyter Notebook to build the model. We log metrics to MLflow. And then once the model is ready, we are happy with the metrics, we'll publish the model to model registry in MLflow. So we'll use MLflow for both logging your metrics, stacking your experiments, and also for model registry. Now you also use DVC to manage your model version. So it's kind of like I said, there were multiple toolings. You can choose whichever is the best, and there could be a better model registry in future also. So and then the other part we won't cover today because of lack of time, but it's important to know, like once you deploy the model, you could use a tooling like Seldon to package your model as microservice and deploy it. Once the model is running in production, it could feed from a live data, which could be a live data stream. And then there are tools like Alibi Detect, which can detect outliers and drift in your data. And it can look for concept and data drift. And then once a drift is detected, based on the AI ethics committee, the decisions made that at this point I will trigger retraining, we would send it back for resampling, where they would go back to the data catalog. And this probably would be more of a manual where data scientists would need to spend time to figure out, resample the data and say, okay, this data looks better, and then use that as a new version of the data. And the process begins again. So this is one view of the data science and the MLOps cycle using some of these patterns. And so let's have a look at it now. So this is my DVC code. So instead of loading a CSV in Pandas, it becomes it adds a few lines of code. So what I'm doing here is I'm setting a version for, say, this is one of the, I'm going back to the 5th version because that was my original data set. And I'm calling the data set, I'm just giving it a data set label version 1. And let me load that data set. So I'm loading that. So now you can see here the original data set is actually in Google Drive, but I'm just loading it using DVC, and DVC is just giving me a gate interface to that. Now, this data set is basically from Kaggle. It's from the Analytics Vidya loan prediction competition. And here we have this fields like gender, married, dependence, education, and the target is the loan status, if the loan was approved or no. So multiple features like loan amount, credit history, etc. And the target is loan status. We are trying to make a prediction. Now you'll see a lot more categorical features here. A few numeric features like applicant income, co-applicant income, etc. So, and then what we'll do is for the categorical features, like just do a plot of how the outcome changes based on some of these protected features. So we saw in the previous session by Mukta where gender and married would be a protected feature, and would we want to kind of would we look at how our decision influences by that. So this is a pure just a direct plot that we did to see how the variance is, and we can see though there is a less number of females, but the distribution seems pretty even, where you can say for the loan status, the number of approvals and rejections look pretty even. Now, this is visually. We can do the same thing using Fairness 360. So we can look at AI Fairness 360 and calculate matrices. So these are the two matrices that Mukta talked about: statistical parity difference and disparate impact ratio. So I'm importing AI Fairness 360 library here, and using the gender and using gender as the field, I'm calculating the statistical parity difference. And you can look at the IBM website. It has very good definitions of each of these terms. So statistical parity difference will just tell you between the two groups how much is the statistical parity, the difference, and this should be between. I think this should be between -1 and 1, and a smaller value close to 0 should be good. So this value is pretty good, and disparity impact ratio should be more close to 1, and 95% is pretty good. So this data set seems to be pretty fair. Now what I'll do is, because I have access to DVC, now instead of loading a new CSV file, I'll just change the version 2 and move back from 5, I'll go back to 4 and load a new data set. So hopefully this will be loaded from Google Drive. Now, these were the original charts where you will see the distribution of the loan status. Let me run this on the new data set. And now you see there is a stark difference in the distribution. Now, a lot more females loans are getting rejected compared to males. So this, visually looking at this, sets a trigger to me. So if I'm an auditor or from the AI ethics committee, if I get a report like this, that my previous data set had a much even data distribution, and then my new data set, the distribution has changed. Now, this is a red alert that, okay, something is going to be wrong with this data set. There may be a fairness issue. Now, let's go ahead with it. Let's consider this. Go ahead and see how this will affect. Now, before that, let's just run the statistical parity metrics also on this. So I'll run this metric. Now you can see that the metrics have changed. So there's a -0.4. So I think it was -0.1 to +0.1 is better for statistical parity difference. So -0.4, that means there is a bias in the data set. Similarly, this one has become very less. From 0.9, it became 0.35, the disparate impact ratio. So definitely there is a bias that we are seeing in the data set. So from the data catalog, what we saw, we loaded 2 different versions without even having to look at files. We just changed the version name. We loaded 2 versions. We could compare the distributions. So this was one of the patterns of data catalog, and then using fairness metrics to look at the distribution and quantify. So first, from a chart, you can see there is a bias, and you can quantify the bias. Now let's go forward. What we'll do is we'll use ML flow for logging this experiment. So I know there may be a bias in this data set. So let's see how my data set performs. Let me go ahead and build a model. So I'm going to connect to ML flow. So I have ML flow running on one of the servers, and I've created an experiment called CODS-COMAD demo. So I'm going to run with this data set on that demo. So first code, this is just a code to connect to my experiment. So what I'll do is these charts of data distribution, I'll log them. So with MLflow, you can log your matrices as well as you can log charts as artifacts. So I'll do that. I'll go and log the fairness matrices. I'll do the pre-processing of the data here. This is standard pre-processing, dropping NAs, doing some of the data normalization. And for this demo, I'm just building a simple random forest model. One of the reasons, because it is inherently explainable. You can do way more, like when you use something like PyCaret to actually build a lot of, do an AutoML, do a model comparison. But for this one, I'm just doing a straightforward random forest. I'll collect the confusion metrics, and then I'll log the confusion metrics, and then I'll generate explanations for this. So what I'm generating here is using SHAP library. SHAP is a game theory based explainer. So it's a post hoc explainer. So it will take a model and run game theory based explanations. It will allocate credit to each of the features based on the result, and it will generate this. So this is a global explanation for the entire model. I'm trying to see which features are important. Now, if you look at it, it says credit history is important, which is great, which is ethically correct. But it says gender and merit become very important for the second and third feature. Now, this tells me that there's a bias. So we saw that there was a hint of bias from the fairness, and now after building a model, that bias from the data went into the model, and the model that I have tested for explainability now has a bias. So this is an example. We saw the data loaded from the data catalog had fairness, has bias issues, and that bias, when I used it to build a model, that bias directly featured here. So now let me log this model and end the experiment. Now I could save the model to DVC also, but I would prefer to save it to MLflow. So let's go to MLflow now. So in MLflow, I'll go to this category of experiments. Now there are 2 experiments because I actually ran the same ML lifecycle with the earlier unbiased data set. So let me look at that first. So this is the unbiased data set version 1. And you can see these are the metrics that what MLflow does is, this is the kind of audit I was talking about. You don't need to run this as a Jupyter notebook. You could have run whatever steps I did as a Jenkins job. So as a Jenkins jobs for a new data set, I could just follow these steps, do the data cleansing, run the feature engineering, and build a model, and then give a report like this to the AI ethics committee or to more of a manager. You can give a report like this in MLflow saying, okay, for this data set, first, these are the data set metrics. This is the disparate impact ratio, which seems pretty good. Statistical parity seems good. Once you build a model, these are the model metrics. Test accuracy is 0.8, which is good. Test FN score is 0.86, which is good. These are the charts if you want to see the data distribution. This was the original data distribution we saw. There's a very even distribution of male and female genders. And then this is the model. So I have also logged the model. Now what you could do here is I could register this model. So I can go to so MLflow has a model registry where I can say, okay, for the loan prediction, let me register this model. So now I can go to the models available here. And this is the latest version 5 of the model. This is in the registry. So now instead of giving that model as a pickle file, the model is available into this model registry. All I have to do is call the registry using MLflow API, and it will download the right version of the model and use it. So now everybody, wherever you are experimenting or deploying, you use the same version of the model from the registry. So this pattern of model registry really helps to standardize and achieve reproducibility, just like the data catalog did for the data set. So the last thing what we look at is these two experiments that we did. So we did on dataset version 2 and version 1. Let's do a comparison. So so this is another thing what MLflow can allow for. So we can look at this and let's do the comparison. So you can see this was the dataset version 1, which we saw did not have bias, and dataset version 2, which had bias. So you could clearly see now compare the disparate impact ratio is 0.35 to 0.958. The accuracy you can see has improved. So the bias dataset did give you a better accuracy, but it had a bias. So this is the human in the loop decision you have to make. You may get a 0.83 is probably small, but you may even get a dataset with a very high accuracy. But then, are you ready to account for the bias? Because bias in the model has translated to the bias in bias in the dataset is translated to the bias in the model. And and then what you could also do is look at this particular bias data set, and you can see the explanations here. So here for this bias data set, gender, like we saw, was an important consideration. But if you look at the older, the first data set version 1, and if you look at its sharp explanations, here credit history, education, property, these are the features it considers for making a decision, now this is what the AI ethics committee would do. Okay, this seems more ethical, so I would approve this model, I would not approve that model. And because you have a model registry, they can decide this model is going to production, this model is not, this model let's hold and rethink the data set that was used to build. So as a vendor, and coming back to the same question, you would want to enable your ML pipeline to have these patterns where you can check for fairness, bias, make these metrics available as an audit, where a decision maker, it could be your decision maker as a vendor or your customer, could make a fair decision based on this. Because when Dr. Mukta showed, the first definition of fairness was fairness through unawareness. You don't really know that your data set is biased. Nobody willingly is going to introduce a bias model. But because of the bias in the data, the bias, the unfairness comes into your model. So you want to check your data set, have the right metrics in place, give an audit report like this, where you can track your metrics, track your fairness charts. And then once the model is ready, do again a cross-checking to see how the explanation, do a global explanation chart like this. And SHAP is just a tool. You could use any other tooling to get the IBM also has multiple libraries. You can, or even Microsoft has libraries for checking these the feature importances. You can check feature importances, see which features drive your model's decision, and then the ethics committee can decide, okay, is this model good enough to deploy to production, and that becomes the human in the loop decision. So this is kind of and then I didn't get to PyCaret, but PyCaret would actually just make it easy for you to build a ML model compared to just sticking to random forest. But it's a pretty popular low code. That's another pattern, low code machine learning. So these are some of the few patterns: data catalog, model registry, fairness metrics, explainable AI. That we highly encourage you as part of your responsible AI system. Whatever tool you want to use, you would want to use this into your ML pipeline, and whoever is the decision maker, you want to present this audit report so that they can take a informed decision free from bias.